Namaste. Welcome to Androidiots Podcast. I am Anupam Singh.
I am Tushar Gupta. We talk about what's new in Android, best practices, and how to be a better Android developer.
Okay, so as you know, there's a lot of things goes behind building an APK, and there's sort of black magic behind what is actually happening, what are the process which is happening behind it. And today we have Romi and Amanjeet from Bobble, and they will shed light up on the same. So Romi, over to you.
Hey, hi guys. So as you might know, the APK that you actually provide to a Android device consists of a lot of files, starting from the manifest to your resource files to the asset folder and the source code as well. So how does the APK gets bundled, and the OS knows that what all things it needs to do to actually run your source code and fetch the files for the same. Okay, so the first process that goes on is the manifest merger process, in which the Java compiler or the Kotlin compiler for the same actually fetches the manifest for all of your underlying projects, your main application, the underlying libraries, and merges them into a single manifest file. During this process, some of the validation tasks are needed. For example, Android needs some components to be present both in the manifest as well as in the source code of the application package. For example, services or activities. So it won't actually validate the manifest unless and until you declare an activity in the both sides, basically in the manifest as well as in the source code. So after the manifest merger happens and you will get the single manifest, it's time for your resources and the assets to get bundled. So all of you might have heard of the command tool AAPT, Android Asset Packaging Tool. So this tool basically handles the packaging of the resources and assets. In the newer Gradle versions it is replaced, but in the older version this is the one which actually handles the resourcing and packaging. So after all this is done, now it comes to the main program, main source code. How the application will actually know and will bundle the source code so that the OS could run it efficiently and without any performance hit. So Amanjeet, over to you. Shed some light over this.
So guys, you are coding your Java files, you are coding your Kotlin files, and some of you are coding both in your same projects.
That's correct.
And you are may thinking like, hey, I am coding both. And what compiler does do after compiling all the Java and Kotlin files? So basically what happens is that the Java C command that compiles the Java code and the Kotlin C command that compiles the Kotlin code, it converts these files to the .class file, which is basically a 8-bit instruction
file format. So yeah, I would like to add something here. So whatever classes you have, be it a private class, a public class, inner, static, any custom class. So the Java compiler or the Kotlin compiler basically will create a single class file for each class declared in your project. Be it, as I mentioned earlier, like be it in any of the following section, like inner, private, static, or public.
So for instance, you have a class ABC and you have an inner class EDF. So you will be having two .class files in this case. So what happens in this .class file is that the JVM parses the .class file. This .class file has some format, and what is it is like, it has header. It has its constant pools of the constant which we are declaring in the Java file. It has the class name, it has the interface names, it has the variable name, what we are declaring. And then these .class files are then going towards journey, which is called dexing.
Okay.
And here is the picture where the dex enters and the dx tool enters.
Correct. So okay, now let's discuss like why is this needed? Because we could have done it with the .class files as well, because as we all know, JVM runs on JVM actually decompiles the .class files and loads them and into the bytecode and actually into the runtime, and actually your application just starts. So what's the need for .dex files and why is it present. So now Android prior to Lollipop was based on Dalvik, and after that it was based on Art, and now it's running on a hybrid model which is using Dalvik as well as Art, because both had their own pros and cons. So Dalvik is another implementation of JVM basically. So underlining, they have the JVM, but so as we all know, like JVM is based on stack based implementation. Any methods, it has a different stack for the method references, and a different stack for the variables and your objects basically. But Dalvik on the other hand is based on registers. So now what happens is, like, what's the difference? In a stack, suppose you are doing A plus B and you are storing the result. So this would require actually some stack operations, stack manipulation operations to actually get the result. Like, it will first fetch the variables from the stack, then pop those two out, add A and B, then store the result back again on the stack. Then whenever you need the result, it will again pop the value from the stack. This would increase the instruction count required to actually process this whole line.
A plus B operation.
The A plus B operation. Now JVM also supports registers, but that is mostly on a counter-based system. For example, you need something like a go-to statement on the bytecode level, so it will use a PC register, we call it, like program counter register. Dalvik on the other hand has its core implementation based on registers itself. Now this brings better performance for the runtime, but it requires more memory, because now you have to store the references of the variables as well, or the methods. Okay. But the plus point, the pro here is you could actually compute the instruction in the operation in one instruction itself, because now you have your variables referenced into the registers, and you could just actually directly access them. So that is why the DEX files are needed for the Dalvik VM, because it needs to understand a different file format, so that it can actually place all these variables or literals or the identifiers or the methods on its VM, so that the application could run in an optimized way.
So it's much more optimized for our mobiles, handheld devices than JVM.
Correct. And it would run faster, but it would occupy more memory.
But what about, say, smaller phones who has less memory, less RAM?
So okay, now consider JVM. Usually JVM, you don't have a lot of processes running and interacting with each other, right? It's okay to not have a fast, a very speedy computation, okay? But it's it's necessary to actually optimize the memory down the line, so that your heap allocations don't cost you too much, your GC revamps don't cost you too much. Whereas on Android, though memory is an issue, but the computational cost is a bigger issue than the memory optimization, because you have a lot of things running on your Android phone at a single point of time. You have your battery managers, you have your activity managers, you have the whole Zygote process running, you have the notification managers, the screen getting on and off, the whole OS running. So there are a lot of things that are running. There are a lot of inter-process communications that are happening. So it needs some way in which So okay, let's consider if Dalvik was made using stacks. What would happen in a case scenario in which you have a simple keyboard and you are just typing something on a WhatsApp chat basically. So now the text is getting comprised in the keyboard app itself, but it's making an IPC call to the WhatsApp's edit input box, which is happening through the Zygote input method manager service, and it will actually send the text to that edit text in which the keyboard is attached to. If this would have been implemented through a stack, again it will pop the input method manager instance from the stack, and make a pop operation to actually get the instance for the method which would actually commit, which would actually make the IPC call to the different application in which you are targeting, to the WhatsApp application basically. And then it would again pop the edit text instance from the stack, and then again send the text to here. So like this is computationally heavy, because you'll have to like pop the reference or pop the instance basically, like each time whenever you go through each class actually. Right. But when you are using registers, all of these instances are just referenced through an index. Okay, so it's like you can just actually have that index and just fetch that. You don't need all the stack manipulation. So this is faster. Though that is why Android GC is different from Java GC.
Yeah.
We will talk about that later also. Amanjeet, back to you. What
else we have?
Yeah.
So basically, one point here which we should mention, the multiple dot class file which Java C or Kotlin C is going to create, that goes into a single dot text file. Not multiple text files are created, only a single text file is created. At the end.
Yeah.
At the end, the file name is classes.tx, classes.dex, which enters in your APK, and then the whole installation process occurs.
So is there an optimization involved while in creating just one single .text file?
Yes, that is why actually the classes.dex was made, because there was an optimization need in this step. Some redundancies were there, like multiple strings are there which have same name.
I would like to add something here. So, when you are generating a class file for each class, right? Your class file have this structure in which it will store all the identifiers. It will have the header. It will store all the methods, the fields, the interface names, the attributes, etc., etc. So, what will happen is while your compiler is generating a class file for each class, there will be a lot of identifiers. For example, a simple string like ABC or a simple string M context, which would be declared like in each activity or in each class. It will have the same identifier. So, but in the dot class file, it will have an entry in each class file, which is not as optimized. I mean, which could be optimized. So, this is one of the optimization that text does. Like whenever it will find something redundant in any of the string literals or the identifiers or the type IDs, it would actually just have single reference for that. Yeah.
And so, as I mentioned, that class file has its own header and all its format. So now the DAX file has been made. So it has its own format and it is longer. Yes, its own header and its own format, which is going to be needed by the Dalvik or ART and being passed by that. First, we have the header of DEX, which actually verifies that it is a text file.
Yeah.
It is basically a magic number. It is a constant magic number, which is an instruction that is passed by Dalvik or ART and is verified that is it a text file or not. And then the later verifications are there and the pass process continues. So, talking about the format, we have header, we have string IDs, we have indexes of string, we have indexes of types, we have indexes of prototypes, we have the fields, we have the methods, and the basically the classes which are entering in the text files. And this is basically parsed by the Dalvik and ART in the later stage. So now we are moving towards the installation. But yes, the road diverges here.
Yeah, okay.
Either it will go through the Dalvik or it will go through ART.
Okay.
And I'll give you spoiler, it can go through the both also.
Which is implemented in the new, since Nougat, I guess.
No, okay.
Yeah. So there is a hybrid road also.
Okay.
Yeah.
So what happens?
And we don't have control over this.
No, you
don't have. Okay. As a developer, I cannot do anything.
This is like a behavior which a platform has. You can't hook up that much.
So
the best way here is to actually keep yourself updated with what's going on. So if some issue arrives, you could actually drive down through the safe with okay, what's happening, or you can actually get some insights on what should be done.
So the process of deciding to go with Dalvik, ART, or let's say the hybrid model, is it dependent upon the OS that you are running or the device that you are running, or something else?
So it's dependent on the OS, basically the Android version which you are running. Okay, so when Android was starting, they made Dalvik, right? They just forked the JVM, made their own optimizations. There's a lot of difference between DVM and JVM, but that's a topic in itself. So generally, while developing DVM, their main thought was to have the applications compiled using the JIT compilation mechanism. Because they thought whenever the because it's justified to actually compile the app whenever the application is to be started, or when the user actually
it's about to
be started. Yeah. But as Android grew, and there were a lot of applications or service mechanisms which would actually start as soon as the OS starts, or you would have your alarm manager set, or a lot of things like which would actually need to be started. For example, some system services which won't need a user action to actually start the application, and which would need the application to perform prior before it's being started. This increased performance. But I mean that's also debatable. I mean there are a lot of threads which go on like JIT was better, AOT was better, and that's the reason why we came to a hybrid model in NuGet.
Yeah, Amanjeet, you were saying.
Yes. So the Dalvik is having its own optimizations also, and the ART is also having its own optimizations. So the DEX enters there. The DEX enters that road of Dalvik. The DEX enters the road of ART, but not the DEX file is going to be installed there. There is a process which is called DEX opt in the case of Dalvik, and there is a process which is called DEX to OT in the process of the road which is going towards the ART. In the process of DEX opt, the ODEX file is going to be made.
Okay.
Now, what is the...
That stands for optimized DEX.
Yes, actually.
The
so
one
that's
you were
why
asking.
the ODEX.
Okay.
Yeah.
The ODEX file.
So though I would like to add here, like this optimization is different from the optimization that DX toolchain made from the .class files to .dex.
Okay.
This is another
This
optimization.
is basically further optimization on the
Text
file.
files.
Yes. So this optimization, the second optimization which we are talking about right now, I mean on the VM based optimization. So this is majorly to focus to make the performance on the runtime better. I mean, Amanjeet would continue.
So in the ODEX file, that is the case of Dalvik, we have a code which is already extracted on the boot up of the phone. So in that case, that is optimized, because if the app is going to run in a future, like Android process will extract the code from there and will run the app. But in the ART way, the ELF file is made, which is like optimized version of the DEX file in the ART system, and that is already kept natively compiled, which like directly goes into the ARM of the phone and will like boot up faster than.
There's one more point to add here. Ahead of time compilation like this, like actually compiling your code earlier prior and into native and actually storing it is very high performant on ARM based architectures, on ARM processors, because internally ARM works the same way. So that's why it's actually it's not that of a performance, because when you start thinking of it, ahead of time compilation should cost you more, because if suppose you have like 100 apps, whenever your OS boots up, you'll have to compile the 100 applications.
This is what I was thinking. If you have more than 100 apps on your phone, as soon as your phone boots up, you're basically compiling each and every app and keeping that.
So you might have noticed that whenever, like if you have the ART-based Android device, so whenever your OS boots, there's a dialog that pops
Loading
up.
apps.
Loading apps, optimizing apps. It's different with different manufacturers, different stock Android versions, but so yeah, it's basically the same dialog. In the hood, the same thing is going on in each of the devices. So now the ARM architecture is highly efficient, to perform something like this, to actually store, something into memory, like parallelly into the registers. So this is why this could actually happen, and this is why, ART actually could make a difference. Not ART, like ahead of time compilation could actually make a difference.
Cool, that's cool.
And the optimization don't stop here only.
Yeah.
Oh, there's more.
Yeah, there's more.
There's more coming. And so basically, ART also does one thing good in an area called GC, that is garbage collection.
Yeah, that's a major improvement.
That's a major improvement by ART, and that the difference is basically two things which are going to be happening here. The CMS process, which I think you are already like.
Are you like familiar of this?
No, we don't lie. We are not.
So CMS is basically concurrent mark sweep.
Okay.
Yeah.
So you use the acronym. Okay.
I use the acronym.
So I don't know the process entirely. Just go ahead.
So concurrent mark sweep, that that
Mark sweep. Some people call it as mark sweep algorithm.
Yeah. Actually, that's the same thing I'm talking about.
Correct.
So in this case, the JVM also has mark sweep.
Yeah.
The Dalvik also works on
both
the
of the GCs are mark and sweep GCs.
Okay.
So you mark the unused one, and then GC will all
Sweep the
clear
references.
sweep the variables.
Weak references, correct.
So in
Weak
this,
references or anything like which is
Software.
Not being used.
Yeah, not being used.
so in the art case, what happens is the thread are assigned their own CMS. The thread of apps have their own CMS running parallelly.
The bigger picture is in Dalvik, the GC handles the marking as well as the sweeping of the objects. So GC as in the system GC. So the system basically handles the marking as well as the sweeping. So it's a 2 iteration based process. Whereas in art, your application is responsible for marking the projects and the system GC will just sweep it down. So it's a single iteration process. So what happens in mark and sweep, your application thread gets blocked, your main thread gets blocked, right? So that's why there's a 16 millisecond window. We all talk about there's
frame
frozen
rates,
frames, etc., etc. In art, it's just half the performance hit, which you get from.
How does application do the marking?
Yeah, so this is what actually Amanjeet was telling. Like each thread has its own CMS process, and Amanjeet, I would like you to continue over here.
Every application has its own thread. It will be going to mark the unused resources of its own, which will be running parallelly
With the application.
with the application.
Okay.
So
That's good.
that will be optimized in the art.
On a scale of a good code base or a lot of services running, a lot of threads running in a multi-threading app.
A lot of difference.
Yeah, this is a heavy chunk of
Heavy lifting done by art. Yeah, that's very cool.
So till now you've only mentioned pros of art, but you're saying that
There's a hybrid model.
There's also a hybrid model involved. They both have their pros and cons. So can you tell me a little about
Any
any cons of art? That why are we going for the hybrid model
Why there is
and
a
not just
hybrid model?
not just art?
Whenever the ahead of time compilation happens, your runtime actually just compiles the main text file that you are using. It won't. So suppose you have like classes.txt, classes2.txt, classes3.txt, but it won't actually compile the classes2 and classes3.txt into the runtime, and it would just have the main text file into it. So what happens is it's like it's AOT, but it's actually not AOT to a complete extent whenever you have multiplexing. So your application will have the main initial classes initialized, etc., but again there's a overhead to if you have multi-text supported application, again there's a overhead which would actually need to compile the classes the secondary text files whenever they are needed.
Okay, that's the con.
Yeah, so that's the con. So it's not actually the full AOT that we think
It's
of.
optimized of majority of the apps, but
Yeah,
not
but
all
not
the apps.
all the apps.
Okay, correct.
Then again, obviously, scale is actually an issue also. Like if you have a lot of applications running, then your application, your OS startup time becomes huge. So suppose every time, so now there's again this issue that we all face in Android, that is software fragmentation and hardware fragmentation, basically fragmentation. So now each manufacturer actually compiles its own Android version and gives it to you, or they have their own hardware SDKs and they do it. So a lot of them make changes to that also. So now while compiling from the DEX to actually the native code, the class loaders basically and the runtime that is used is also not that great is also not that reliable that we think of. Okay, so I mean there are cons in that also, like it won't actually load it properly if there's like too many files to load, or it will optimize, like it will load half of the application in the first iteration, it will load half of the application in the second iteration. So then the OS startup time increases. So and if the OS there's an update for the OS, there's a lot of interest that goes on. So it's not very reliable also.
And in behind the scenes, there is also like when the app is in the cached state or background state.
Okay, so Art only has this feature. Okay, Dalvik didn't have this feature.
Art is having this feature that is called heap compaction. So when your app is in the background state or cache state, there will be like a GC calls there also.
Yeah. So this is another one of the GC improvisations that Art did.
Okay.
So yeah, continue.
So heap compaction.
Okay, so in Dalvik, what used to happen? Suppose you had like 4 or 5 GC calls, and each GC call like saved you like around 5 MBs of some memory. So now so you have a heap, right, in which your application runs, like in which all the literals and the values and the variables are actually stored. So though for native primitive types you have a different native stack, but let's talk about that later. I mean, now in the heap, whenever the GC runs, GC sweeps all the memory, cleans the memory, and like each GC call like gives you around 5 MB of memory. It will be a distributed memory allocation. It needn't be a continuous allocation. This is how Dalvik runs. So like whenever you have like in this scenario you have like 5 MBs each. So if you need like 10 MBs, you wouldn't actually have the 10 MB right now because
the free memory is basically distributed in a lot.
Correct.
So you can't have a contiguous section.
Exactly. But this is something that Art did. That Art actually thought of it that this needs to be done. So this is the heap compaction that we call. I mean, this is what we call heap compaction.
So in Art, we'll basically have a contiguous 10 MB.
So it's like if 5 GC calls and 5 MB memory sweep done in each of the GC calls, you will have like 25 MB. I mean, it will try to make a continuous block. It needn't be always, you won't be sure like it will always have a continuous memory clause, but to a great extent, it would actually give you one. That's a lot of cool.
And this is going to be done in like background state, so it must be having some cost to like the phone performance because it is going to be done in background. So you don't have any like hand on that. So it will be going to happen. You can't stop that, and battery is going to like some cost of battery is going to drain in that.
So that's also there.
So there are only some components which can invoke this heap compaction. One of them is activity manager. So whenever that managers feel like I need memory.
I think it's because activity manager knows when your app is in foreground or when is it in background.
Yes.
So as soon as it goes in the background, it would actually like mark the objects and be ready. Like this is GC call should occur and like. These are my objects, and you could actually just
it
will pre-prepare the allocations to be made. So that is why it could actually, your GC could actually make a contiguous memory allocation because it's a pre-compiled markdown system.
Okay, I guess with that we wrap up our part 1. Today we learn Android build process, all the nitty-gritties behind it, and all the background optimization that Android does behind the scene. In upcoming part, we'll learn what is multiplexing, its pros and cons, and how can we leverage it better with Romi Chandra Amanjeet. Cheers.